So that we can measure the current in the primary, IP, I've put a resistor in the circuit here. It's a small resistance, it shouldn't affect the behaviour of the circuit, 1.5 ohms. Nothing special about that, I just happen to have a resistor of that value lying around. The current in the primary will create a small voltage across this resistance in accordance with Ohm's law, V equals IR, which will of course be in phase with the current in the primary. And I've sent that now to channel 2 of the oscilloscope. Notice here that the secondary is not connected to a load. We're simply looking at the current flowing in the primary. There is no current in the secondary. Let's have a look at the waveforms. Here we've got the voltage in the primary, and now the second trace shows the current in the primary. You might be forgiven for thinking that there isn't any, but the current is rather small and I have to increase the sensitivity to see it. It's only a few milliamps. It's perfectly clear that this waveform of the current in the primary is indeed out of phase with the voltage in the primary. And of course the current in the primary is what creates phi, the magnetic field, the magnetic flux. If I try and match up the waveforms by altering the sensitivity so that they have the same apparent amplitude, you can see that they're out of phase. And if you look carefully at the screen and start doing square counting and that sort of thing, you can see that the magnetic flux, that is produced by the current in the primary, there's the current in the primary which I'm moving up and down, the current in the primary is 90 degrees out of phase. In fact, it's 90 degrees behind, lagging the voltage in the primary. With no load connected, and that's very important, the current in the primary is out of phase with the voltage in the primary. And in fact, the current in the primary is in phase, almost by definition, with the flux phi. It's the current in the primary which creates the phi, which induces the voltage in the primary, which is out of phase with that current. And of course the voltage in the secondary is out of phase with this current to the same extent, so that the primary voltage and the secondary voltage are in phase. It's the current in the primary that makes the magnetic field, not the voltage. Here we are again looking at the current in the primary waveform, the voltage in the primary waveform. I'm going to reduce the sensitivity because we're going to connect a load to the transformer so that all the currents increase. I'm going to reduce the sensitivity of the scope so that we can just see the very slight current flowing in the primary when there is no load on the secondary. And here, I hope, comes a nice big surprise. When the load is connected, a current flows in the secondary, and a current now flows in the primary, which is much bigger than the current that there was before, and it's almost in phase. Now that the transformer has a load connected, the primary current and the primary voltage are nearly in phase. If I do the matching trick, which I've done before, of changing the sensitivity and trying to get the waveforms together, you can see that the primary current and the primary voltage are now nearly in phase, now that we have a load connected. Let's go back to the phase diagram showing the primary voltage, the secondary voltage and phi. The voltages in phase with one another, each of them out of phase with phi. But the situation now that we have a load connected is made more complicated because the current in the primary produces a magnetic field, a phi, and the current in the secondary also creates a phi, and the phi, the secondary current, the phi produced by the secondary current tends to oppose the phi produced by the primary current, and that's something that we express with Lenz's law. let's have a look at the phase diagrams of the two components of phi which make up this overall resultant phi. We have a phi produced by the primary, and we have a phi which is almost equal and opposite produced by the secondary, so that we get this resultant. There is the phi that we would get if only the current in the primary were acting on the magnetic core. And here is the phi in the secondary, and it's almost equal and it's almost opposite in phase. And that produces a resultant phi here, which is what induces the voltages. What does that mean about the primary current and the secondary current? Well, the primary current is going to be in phase with the component of phi produced by the primary coil. And there it is. There is IP, up there. But the secondary current is going to be parallel to this vector. I'm going to draw it down there. There is the secondary current, almost opposite to the primary current. The reason that we can say that these two are opposite is that the primary is a place where energy goes into the transformer, the secondary is a place where energy goes out of the transformer. So although the voltages are in phase, the currents are in exact antiphase. This means that the current in the primary is in phase with, if you remember, the voltage in the primary and the voltage in the secondary. And the current in the secondary is in exact antiphase with those two. Let's just go back to this diagram over here. If we say that the current in the primary is that way, as it were going down into the primary, the current in the secondary comes out of the secondary. Well, let's reverse the direction of that arrow and measure the current in that direction. Now let's get back to the phase diagram, remove all the stuff about phi, which is internal to the transformer, and now when we look at the currents, having made that phase reversal of the secondary current as measured, we find that the secondary current is in phase with the primary current, or if you like, without doing the minus sign, without doing the reversal, in exact antiphase. And what's more, both of those are in phase with the voltage on the primary and the voltage on the secondary. The upshot of all this is that a proper understanding of Faraday's law and the induction of voltages caused by currents in transformers, the fact that the currents in the secondary and the primary tend to oppose one another because of Lenz's law, the upshot of all of this is that the primary voltage, the primary current, the secondary voltage and the secondary current in an actual transformer and in an ideal transformer properly analysed are all in phase with one another. Nothing is in 90-degree phase with anything else except for the magnetic field inside the transformer. That's your lot.